Hi everyone, my name is Forough Ismaili and I'm a university professor with over 10 years of experience teaching econometrics. In this channel, I'm excited to share my knowledge in a fun and engaging way, bringing you the key concepts and methods of econometrics in a fresh and accessible style. Whether you are a student, a data enthusiast, or someone looking to deepen your understanding of econometric methods or models, this series is designed just for you. Today we are starting with one of the most fundamental techniques in econometrics, the ordinary least square, or OLS regression model. Let's dive right in. OLS, or ordinary least square, is a technique used in linear regression. It's so important to estimate the relationship between one or more independent variables and a dependent variables. Means that one or more dependent variables means yt, alpha plus beta xt. It's independent variable and it's dependent variable. Simply put, it finds the line that best fits the data points by minimizing the sum of the square differences between the actual values and predicted values. Actual values means alpha and beta. Predicted values means alpha hat and beta hat, and so on. This is the core idea that we are going to focus on in this session, and I'll make sure to explain it truly so you can really understand how it works. The primary goal of ordinary least square OLS method is to minimize the errors, minimize the errors, when we estimate alpha and beta, we have errors. So the goal is minimum errors. The difference between the actual values and the predicted values. These differences are called residuals. This means residuals. OLS aims to find the best fitting line by minimizing these residuals, which means finding the line that makes the prediction as close as possible to real data. For example, let's say they have the following scatter to clear the content, x and y. We have some data that we show with a scatter point, and this is the scatter plot. The variable x, for example, represent education. And the variable y represent the wage. What we are trying to do is understand how education affect wage over time. As you can see in this scatter plot, there is a curious trend showing that as education, represented on the x-axis, increases, wages shown on the y-axis also tend to rise, which means that this line, for example, this positive relationship indicates that individuals with more years of education generally earned higher wage. In our analysis, we aim to quantify this relationship using the OLS regression model, allowing us to better understand the impact of education on wage levels over time and over many different education levels. By applying the OLS regression model, we can determine the relationship between these two variables and see how years of education might influence the wage as person earns. In simple linear regression model, the education we use is y equals alpha plus beta x plus epsilon, which means t. Y represent the dependent variable, and in this case is wage. X representing the independent variable, and in this case is education. Alpha is the intercept. Intercept variable, alpha, and which means that when x is 0, y is alpha. Beta is the slope of the line, is beta, is the slope of the line, which tells us how much y or wage changes with a 1 unit increase in x. And the most important is epsilon. Epsilon is the error term capturing the differences between the actual and predicted value. For example, for that point, we predict for 1 point, but the actual is that. It's the difference between the predicted point and the actual point. So this distance is error, and it's the epsilon. It also accounts for factors that are not included in the model but might still is important for the wage. For example, this could be things like experience, personal skills, or other unobserved variables that influence wage, but we do not enter in the model. In this case, we are trying to estimate how change in education level that affect wage by finding the best fitting line using the OLS method. We may have some line, for example 1, 2, 3 or other, and which line is fitted for the data which we have measured. Let's assume that this line, for example 2, is a good fit for the data. Now we need to measure the errors. As I said before, to do this, we look at the vertical distance from each point, to the line. Point above the line have positive errors, and point below lines has negative errors. Our goal is to minimize these errors to get the best fitting line. The first idea is to simply add it. Add up all the errors and choose the model with the smallest total errors as the best one. So far, the data we have shown shows the errors for each point based on the current line we've drawn. You know, for example, if you want just sum the errors, for example, that or that, so we have to minimize the sum of errors. But let's compare these two plots, these plots and these plots. Visually, which line do you think fits the data better? One or two? Which one seems to represent the trend in the data more accurately? If you want to rely on a visual inspection, which line would you choose as the best fit for the data? The correct answer is line 1. Yes, you're right. However, if we only focus on minimizing the sum of their errors, you know, the first line might seem do not better, for example, for example, like that, like that, but the second line, as you see, we have just negative errors. The second line has many negative errors that could cancel out, for example, the positive ones, like that, for example. This would result in a smaller total error, but visually and based on the actual relationship between the data, this line is clearly not a good fit, not a good fit. So just summing the error does not always give us the right model. Now a natural question arises, why don't we just sum up all the errors? Won't that give us an idea of how well the model fits the data? Well, the issue with simply adding the errors is that some of the errors are positive and some of are negative, for example, like that. For example, like that. We have some negative and positive, for example, positive or negative, like that, or negative and positive, like that, positive, negative, like that, and the sum of error, 0. you know. So if we just sum them up, they might cancel each other out like that. This would give us a misleading result, making it seem like there is no error at all, even though there might be significant differences. We should look for a different approach where the errors are evaluated based on their magnitude and impact rather than just their sign. Another possible For example, another possible approach could be to take the absolute values of the error and the sum of, for example, the absolute values and the absolute values, of the error and then sum up. This would avoid the problem of positive and negative errors canceling each other out, or misleading, or getting to error or something like that. But while this is a valid approach, it has some disadvantages in mathematical optimizations. We have to minimize the sum of errors, and in that case, the absolute errors. Taking the absolute value is not as smooth or continuous as squaring errors, and it makes it harder to apply standard calculus techniques for finding this minimum. That's why we use the sum of square errors instead, We use the sum of square errors instead. I square. It also considers the outliers and data points close to reality with equal weight for the absolute value, but the sum squares is not the same way. Instead, OLS minimizes the sum of square errors, which means we square each visuals before adding them up. Squaring the errors has several disadvantages. One is ensure that all errors are treated as positive, All errors are positives. Avoiding the issue of cancelling or cancellation between positive and negative errors. Second, squaring the errors places greater emphasis on large errors, It can emphasize large errors, which is useful because we want to penalize big mistakes more than small ones. Lastly, minimizing the sum of squares leads to a mathematically smooth and solvable optimization problem, So it's useful for mathematics. Allowing us to find the best fitting line using calculus. So, by minimizing the sum of square errors, OLS ensures that we get the most accurate line of best fit while addressing the issue with both adding the errors directly and taking the absolute values, So we have to minimize the square errors, sum of the squares. In the upcoming videos, we will explain how to calculate alpha and beta with this approach. So have a great day.